Some of you may have heard of the EPRI Handbook. If not, I'll give you some background about what it was and what it is in its new incarnation. And I want to acknowledge my collaborators and co-authors here. I know a lot of you know Bob Dodds. He's a longtime professor of civil engineering at the University of Illinois, now retired, and then Thomas Desane and Greg Thorwald contributed in significant ways as well. So, what was the EPRI Handbook originally? Well, back in the 1980s, EPRI, which is Electric Power Research Institute, decided that it would be a good idea to develop a handbook of elastic plastic crack solutions to go along with the solutions for stress intensity factor. Back in the 70s, there were a number of hardbound books that contained K solutions, and those are all out of date now, but there's a few collections around that for stress intensity solutions, and obviously AFGROW has its own library of K solutions that were obtained from various sources. But the need was, and the desire was, for elastic plastic solutions like J integral and also various displacements. And the original authors developed a methodology to estimate J, to first run J finite element solutions and then fit them to an equation. So the estimation procedure involved estimating elastic J from the K solution and then adding a plastic contribution from FEA and then fitting that to an equation. Now, it was a nice idea, but it wasn't practical, certainly in the 1980s, because of computing capabilities. All of us probably carry in our pocket or in our smartphones a more powerful computer than was available in research or institutes, government labs, and so forth to run computational problems back then. So the original EPRI handbook, published in 1981, and the contractors were from GE, was restricted to just some simple 2D configurations, and really nothing. A two-dimensional geometry doesn't really help to analyze structures. Later in the decade, there was a 3-volume set that was published. It purported to contain a bunch of solutions, including some 3D cases, but there's really no way that those could have been based on FEA, because there was no ability to run those types of models with the computing resources. And so it's very mysterious as to where those so-called solutions came from. And because when anything was checked, when the FEA was available, it was found all the solutions that there were pretty much were found to be wrong. And so that effort was never really viable, even though I think people used it over the years, but you really couldn't rely on what was there. Well, fast forward to present day, and obviously now our computing technology is much different than what it was in the 1980s. And so myself and the colleagues on the title slide embarked on a new project funded by EPRI to develop the handbook the way it's originally envisioned. And this involves, as you might suspect, a massive finite element study. And to date in this project, we've run nearly 20,000 three-dimensional elastic plastic simulations and fit those to equations. Now, as part of this project, we came up with a new equation for fitting J solutions, because the old approach had some issues with it. In this first edition, which we're just getting ready to come out with, it's limited to a handful of geometries, just plates, cylindrical shells, and then a piping elbow connected to a straight pipe. And the reason why the cylindrical shells and the elbow to pipe geometries are prioritized is EPRI, of course, supports the power generation industry, and so their structural components of interest are pipes and pressure vessels, and so that's what's prioritized. In the future, other configurations could be added, and the methodology we're using to generate solutions could be applied to, say, airframe components that are of interest down the road. It wouldn't, presumably the work wouldn't be funded by EPRI, but if the industry decides it wants to embark on elastic plastic crack solutions, and that we've come up with a methodology and a workflow procedure that would allow that. So in the handbook, we've got solutions for the J integral. We will have some load lines displacement solutions in the next edition, because that will cover some laboratory specimens. But with most structural component geometries, the load line displacement is not really a relevant quantity. But we're all computing and tabulating the crack mouth opening displacement solutions and the crack opening area solutions. So a little bit about the parametric equation. We tried to make it somewhat physics-based. And so if you look at the deformation of a cracked body, at low loads, you have linear elastic conditions. And then at intermediate loads, you'll have a plastic zone that's contained inside elastic material. And then you'll have the fully yielded ligament. And we know that under linear elastic conditions, the elastic J is proportional to load squared. And under fully plastic conditions for a power law material, this is what's called the Ramberg-Osgood stress-strain equation, where you assume a power law in stress. It was shown in the original EPRI work, the fully plastic J is proportional to load to the n+1 power, where n is a hardening exponent. Now, in the contained yielding region, you can do some back the envelope theory, and you can also run some FEA models, and you can observe that the plastic component of J in the contained yielding zone is a power law in load, but the exponent is neither 2 nor n+1. It's typically something in between those values. Now, the original EPRI handbook just used an Irwin plastic zone correction for that contained yielding zone, the transition between linear elastic and fully plastic. And it was kind of a Band-Aid fix that it was an afterthought, really, and it doesn't work very well. So we abandoned that approach and came up with something a little more robust that fits the finite element solutions much better. So here's what the equation looks like. So we have a J is proportional J elastic times the terms that depend on loading. So this sigma ref is a reference stress, which is a geometry factor H1 times the nominal applied stress, and there's a yield over modulus adjustment. And then we have additional fitting constants. We have beta 1, M1, and gamma 1. So these are fit to the finite element results and then tabulated in the handbook. So, and the first term the middle term in this equation captures the fully plastic J. And then the last term captures the contained yielding zone. And it has, if you care about the math, at low applied loads in this term is significant, and the fully plastic term is small, because n might be a big number like 10. So this is stress over yield raised to a large power. So it's a very small number below yield, and it can be a very big number above yield. And so the functional form here is such that as we get into the fully plastic conditions, this denominator causes this last term to disappear, and then the middle term takes over. And in terms of plotting the results, it's convenient to plot J integral results in what's called a failure assessment diagram. If you've seen some of the fracture codes and standards like API 579 and the British standard BS 7910, you may have seen this diagram before, but if you have it, it's just simply a non-dimensional way of plotting a J integral solution. So if you take the elastic K divided by the K computed from J, which is equal to the square root of J elastic over J total, that the failure assessment diagram, this dimensionless curve, will tail downward. And it's just convenient for fitting because when you're fitting a monotonically increasing KJ or J solution, then what happens is that the very large values get weighted more in the regression than the smaller values. This is, it just gives you better fitting. Here's a couple of examples of fits to FVA results. And the J versus load curves, when they're plotting these dimensional coordinates, do depend on geometry. You see this has a kind of a gradual tail, and then this other curve, this is a crack that's 20% of the wall thickness. And here's one that's 60%, and the curve does have a different shape. And you see that the function does do a fairly good job of capturing the shape. Here's some examples of meshes. Again, we've run about 20,000 of these, so we have to have a way of producing meshes quickly in an automated sense. And so we use commercial software called AFGROW, which was developed at Quest Integrity. Actually, it was originally developed by my consulting company that I had from 1995 to 2007 before I sold it to Quest Integrity. And so it was, but it's so I no longer own this software as in terms of the intellectual property, but I still use it in my everyday consulting work. And so here's a circumferential crack and an axial through wall crack and a long axial surface crack. And these different colors correspond to different, you can assign different material groups here for doing a weld. And so I use the weld geometry just to help affect the mesh around the crack. So we have lots of nice regular element shapes there. So this is just 3 examples out of the tens of thousands that we've done. So how do we do this? How do we generate 20,000 solutions and then fit them? Well, as I mentioned, we build the mesh with the FEA crack software, and then we use the Warp 3D finite element software to solve it. Now, as I mentioned Bob Dodds at the beginning of this, those of you who know him know that he and his students and his postdocs over the years developed Warp 3D, and it's open source code that you can download and look at the Fortran source code and modify it if you feel like it. And so, because Bob is the godfather of Warp 3D, for this project, he went and made some modifications such that when you're doing a crack problem, the software now can calculate what the next load step should be based on how much K and J change in each load step. If you run any elastic plastic analysis, you know that one of the challenges is trying to define the load step size. And if you're doing a whole bunch of crack meshes with different size cracks, you know that all meshes can't use the same load stepping. So it saves a huge amount of time and effort to be able, for the software itself to be able to be able to once you give it the starting load, then it will then figure out what the next load should be, and so on and so forth. So it gives you a nice number of load steps with roughly evenly spaced points that are appropriate to fit. And then as part of the infrastructure, basically what we made here is a J integral factory. We built this factory rather than manufacturing widgets or some other part, we're manufacturing J solutions. And so we have the mesh generator, we have the solver. There's various Bash and Python scripts. Most of this work is done by Bob and for editing the input files and duplicating. For example, I'll generate a mesh for a given crack size and geometry. Then Bob will take that and run his scripts. It will then make copies of that mesh and put the material curves in with different strain hardening exponents. You also put in the syntax that's needed for the automatic adaptive load stepping. And then he's got code for batch processing and queuing jobs, and then another set of scripts for post-processing and running various QA checks on the solutions. And all of the computation is done at the Ohio Supercomputing Center at Ohio State. Now, there's two main advantages to using Warp 3D versus, say, Abacus or ANSYS in this project. One is that we have access to the source code, and so this adaptive load stepping is not something that's available to you in Abacus or ANSYS, because you as a user can't go in and tweak the source code and introduce this feature into it. Whereas Bob is the overall developer and supervised students and postdocs developing it, so he was able to write this himself. The other huge advantage is it's free. So imagine trying to run multiple instances of Abacus simultaneously, where each instance is using a whole bunch of processors, and you're talking about licensing costs that would rival the national debt. So this is, that we pay for computer time at the Ohio Supercomputing Center, but that's actually very, very reasonable. It's they're very reasonably priced. So we could do a lot of computation for tens of dollars or hundreds of dollars. Once we have all these solutions, then we have to fit them to the parametric equation, and that's a lot more difficult than it might sound. It's not a matter of just running through and do a regression. We're generating tables of these four coefficients, and when you have four parameters in a fit, there's not a unique best fit. There's a large number of combinations of these four variables that will give you a reasonably good fit. So we're not necessarily looking for the best overall fit, because we want to have coefficient tables that allow you to interpolate within those tables to get these values. Because if you allow the regression analysis to try to find the best fit, then each one of these parameters are not going to very smoothly. They're going to jump around, and so you can't interpolate on the coefficients. So there's been a lot of effort in optimizing the fitting algorithm so that a given parameter here is H1. We make sure that in multidimensional space, the parameters vary smoothly or monotonically. And then the results are plotted as this dimensionless failure assessment diagram. We make sure that the fits are smooth and continuous from the discrete solution. And they use a radial basis function. And if somebody asks me what that is in the Q&A, then I won't. I can't even pretend to know what that is. So that's Thomas Desane who is taking care of that. So I just know that they worked really hard at trying to tune this fitting algorithm, because it has to prove to be very challenging in order to have these coefficients that can be interpolated. So I mean, I know you can't read this, but just as just a illustration, this is one of the tables. After the fitting, then the data is then put into Excel sheets, and they've written the scripts that format the Excel sheets and put the data in there, so there's no manual copying and pasting. And in the report, which will be, when it's published, it'll be a PDF. the readers of the report will be able to access all these tables by clicking on links and pulling up the Excel files. So this particular spreadsheet here has a bunch of tabs. Again, I know you can't read it, but it's there's the tabs correspond to the hard, like there's n equals 3, 5, 7, 10, and 15. And this has to be a semi-elliptical surface crack. So there's solutions for phi equals 0, the free surface, and phi equals 90. So again, this one Excel file has 10 tabs in it. And then I've only just given you a short snapshot of this table. It goes on for much longer than this because we have one of the variables is the radius over thickness. So we have the geometric variables, the crack dimensions, and then the various coefficients that are tabulated here. So the nice thing for the end user is that if they want to actually apply this, they don't have to look at a static text word table and then have to re-enter the data, which is a process that's guaranteed to generate errors. So the end user will have access to the digital data in Excel sheets from the report. So where are we on this? Well, the first edition of the handbook and the corresponding solutions has been completed and is in final review. There's some work as a result of the review. We found some unusual trends in some of the fits, and so the fits are being redone and refined. But the handbook is finished, but is just being finalized. And there's, I wrote a prototype app with Excel VBA that where we loaded in all the tables, and I programmed the basic equations and can do just basic crack stability calculations with these solutions. And this is certainly not a commercial grade software app. It's mainly to, as a first thing, just to test all the solutions and just run them through J analysis and make sure there's no funny trends that we didn't anticipate. But also for EPRI members who buy the reports or get the report as for being members, then this app will be part of that. And down the road, there may be a project to develop a commercial grade software app. And then there's certain geometries that we haven't yet, that we plan to include but haven't yet included. So in 2025, we're planning on doing a series of additional solutions and then updating the handbook. Now, I know one question that people might ask me is, well, where can you get a copy of the EPRI handbook when it comes out? First answer is I'm not sure. The second part of that answer is it's likely that it's not going to initially be available to the public even for purchase. That eventually will change, but it's something that I don't have any control over. EPRI will decide what they want to do. It'll be made available to its EPRI members, which is probably your local utility is very likely an EPRI member, but not to the general public. However, there's a related project that's going on now, and as a result of all of it, Bob and myself and others, as a result of us having built this J integral factory that allows us to generate J solutions very quickly and then fit them, I'm working on, along with Bob and Thomas, a set of solutions that's going to go into the API 579 fitness or service standard. We're going to do what's called a level 3 J-based method for API 579, and based on finite element solutions. And the standard failure assessment diagram, we're going to improve the plasticity axis on the failure assessment diagram with FEA as well. Now, It's going to be similar to the EPRI solutions, except we're using a slightly simplified or dumbed down equation. I mean, these equations look alike, but there's the EPRI equation that is being used in this project has 4 fitting parameters, whereas in the 579 we're reducing that to 2 terms. So this exponent here, this exponent here is a variable in EPRI, and it's set to 2 here, and then this gamma is a variable, but it's simply set to 1 here. So that makes it'll make it simpler for the users of the API 579 standard. So this will be publicly available through the various sources where you buy codes and standards. So I believe that's my last slide. So with that, I'd be happy to answer any questions you may have.